Okay. So we're still talking about method of steepest descents. And the general idea of this method is that you have some integral of the form I of x equals, make sure I have the right, okay, equals some integral over a curve in a complex plane, f of t e to the x rho of t dt as x goes to a positive infinity. And the idea is that you want to find for rho complex and f complex the regions where you have critical points of rho of t, or the place where you have a critical point of rho of t, in particular where the imaginary part of rho of t is constant along some contour passing through that critical point, and where the real part of rho of t descends essentially like a Gaussian does, and the steepest possible Gaussian that you could have there. Okay, so we're looking for critical points of rho of t that are saddles in the complex plane. Okay, and so the general approach that we outlined is to first identify the critical points of rho, then find our steepest descent paths, okay, and we call these CS. And the third is to deform C onto CS. So essentially draw a contour that includes C and CS. It's closed. And then we can use Cauchy's theorem in order to identify the value of that contour integral, and then also the value of the integral along the steepest descent curve will just be given by your typical Gaussian integral formula, okay, using Laplace's method. Okay. All right. And the example that we started in on was that the integral from minus a to a of I x t squared dt as x goes to positive infinity. And what we found is that our steepest descent curve is going to be this one in the complex plane if we write t is equal to u plus iv in this case. And then there's this curve that we want to avoid. This is u equals minus v. Okay. And the reason this is steepest descent is because that's where our function it squared is going to be constant in the imaginary part, and it's going to be most steeply descending in its real part. Okay, so we sort of wrote this out in that case. Right, our rho of t in that case is it squared, right? Or d rho dt equals 0, where this t0 equals 0. And this is our saddle point, okay? our imaginary part of IT squared is equal to u squared minus v squared equals 0. That's how we got u equals plus and minus v as our possible steepest descent directions, okay? And then local analysis is basically going to separate steepest ascent and descent. Because you could have, multiple candidates for the steepest descent curve. In particular, if we take, in this case, d2 rho dt squared of t0, that's going to be equal to some constant a times e to the I alpha, right? Now, what's our alphas in this case? If we go back here, it could be pi over 4, it could be 3 pi over 4, it could be 5 pi over 4, it could be 7 pi over 4. That's all of the angles of these directions emanating from our saddle point here, okay? So if we look at the approximation, right, rho of t minus rho of t0 here, it's going to be approximated in this case by r squared over 2 now times e to the I n theta times e to the, sorry, in particular for this, it's going to be 2I theta, right? Because that's just squaring the argument t in that case. If we write t equals r e to the I theta, right? E to the 2I theta times e to the I alpha, which is equal to r squared over 2 cosine of alpha plus n theta plus I sine alpha plus, writing n, but we're looking at the specific case here. 2 theta then, okay? So now we see, right, if we want something that's Gaussian-ish, we have two conditions that we need to be satisfied. We want the imaginary part to vanish, right, because the standard Gaussian doesn't have any imaginary part in it. And we want this part to be -1, okay, because that's as steep as we can make a quadratic function, right? We want a nice quadratic function with a peak tailor-made for Laplace's method, okay? So then our conditions here end up being sine of alpha plus 2 theta equals 0, and cosine of alpha plus 2 theta is going to be less than 0, but we can make it equal to -1 in this case, okay? And if we take, right, alpha equal pi over 4 in this case, then we have that theta can be equal to minus alpha over 2 plus pi over 2. In other words, in this case, that's going to be equal to pi over 4, where theta is equal to minus alpha over 2 plus 3 pi over 2, which is equal to 5 pi over 4. Okay, so that's how we get those two steepest descent directions. Okay. Okay. So that's the kind of geometry of the complex plane that we have to deal with. Okay. Now the next step is to deform C so that we involve the steepest descent contour in our contour integral. Okay. So now we're going to deform C to our steepest descent contour, C prime. Okay. Essentially the union of steepest descent paths, okay, along which, the imaginary part of rho is equal to the imaginary part of rho at t0, and then we also have this steep fall off in this case. All right, so we worked this out last time. I'm just sort of ramping us back up and sort of reviewing this. So we have U, V, now have this steepest descent path here. I'll label this C1 and C2 here. Here's our minus A and A here, okay? And that's our T0 there. This is our original integral runs along the real axis there, okay? And so the integral in C1, I x t squared dt, we can approximate this as just the integral over some short segment, right? E to the I x I r squared e to the I pi over 4, which is going to be equal to integral from 0 to epsilon with an e to the I pi over 4 out in front, e to the minus xr squared dr, okay? And then we can do our series of approximations, right? The typical Gaussian integral approximation. Integral from 0 to infinity of e to the minus xr squared dr, right? And then if we do change of variables and our Gaussian integral, we get a half square root of pi over x, e to the I pi over 4, okay? Now we can do something similar along C2, which is kind of the other half of our steepest descent curve, okay? It's the other side of it. So along C2, we would have T is equal to R e to the I pi 5 pi over 4, right? Because it's along this direction now. And in that case, we have the integral over C2 e to the I x t squared dt is equal to minus integral from 0 to epsilon e to the minus xr squared dr e to the I pi over 4. And by the same token, we can approximate this as minus a half, okay, square root of pi over x e to the I pi over 4, okay? Now, we're going to extend this and drop this down here. That's our deformation procedure that allows us to use something like Cauchy's theorem. And notice that now along this way, we have to sort of go the opposite direction that we went in order to do this original integral. So we need to flip the sign. This one is fine. We can get a nice closed contour following the direction that we just took along C2, okay? So now Cauchy's theorem tells us the following, okay? That the integral along C plus the integral along what I'll call C3, call this one C4 over here, plus the integral along C3 minus the integral along C1 plus the integral along C2 plus the integral along C4 of e to the I x t squared dt should equal 0 because we have no singularities of our function there, okay? So now this is where we sort of stitch together concepts in complex analysis, right? No singularities, no poles within here, no poles within here. We can do these closed contour integrals. I can carry out this integral. I can carry out this integral by method of steepest descent, okay? This is the integral that I want to know, this one that lives along C here. Okay, what about this C2 and C3 and C4 now, okay? Let's take a closer look. I of x is equal to integral over C e to the I x t squared dt equals the integral over C1 minus C2 minus C3 minus C4 now e to the I x t squared dt, okay? And our claim is that essentially we have everything we need already, and I'll prove this, not prove it, but sort of justify this shortly, that I of x to leading order can be approximated by our saddle point integrals that we've just done. These sections are not going to provide a contribution that is as substantial as this leading order approximation, okay? Because we are drawing a line through the saddle points here, which should be the saddle point here, which should be the largest contributor to our integral, okay? These should not contribute at all, okay, to the leading order approximation. So my claim is that this difference of integrals here approximates the integral that we're interested in appropriately, and that gives us the square root of pi over x e to the I pi over 4 as x goes to positive infinity, okay? Now, now to higher order, we would have to include the integral on C3 and the integral on C4. And for this, okay, we could follow our derivation from the stationary phase section, okay? But the biggest point is that on C3 and C4, there are no saddle points, okay? So that means they're higher order corrections, okay? And so we have everything we need just at the saddle point. And this is typically what happens with the steepest descent method. Once you go through the saddle point, the other sections of your contour integral that you need to include in order to stitch together your contour to your deformed contour are not going to have as large of a contribution as the saddle point portion will. So you can just say, well, I will drop those in my leading order expansion, okay? Now, if you want to go further, you can use integration by parts to get the full asymptotics, right? And you can expand your amplitude out. You can expand the series in your exponential argument out, okay? And check that they are higher order, okay? So in this case, on C3, right, if we look at t equals a plus iv, where v goes from 0 to a, then we have that the integral over C3 of e to the I x t squared dt is equal to the integral from 0 to a of e to the I x a plus iv quantity squared integrated with respect to a plus iv. Okay. So I can show that they're higher order by saying, well, if I take the magnitude of this integral and I bound it from above, I'll get an integral from 0 to a of e to the minus x 2av dv. This is equal to 1 over 2ax times 1 minus e to the minus 2x a squared, okay, which is going to be of order 1 over x, okay, as is the integral over C4. So in other words, okay, we can show by this bounding argument that those terms are going to be higher order. Okay. All right, so that's the first example of using method of steepest descents. Any questions about this? Okay. All right, I'm gonna try and do at least one more example. You'll have a chance to do a couple steepest descent examples on your homework. If I don't get through the second example, I may just record it as extra for you all to take a look at. All right, so let me do another example now. And I'll take the case of the following integral. I of x is equal to the integral from minus infinity to infinity, e to the I x t divided by 1 plus t squared to the x dt, okay, as x goes to positive infinity, okay. Now, first of all, I can go ahead and write this as an integral that's kind of in that convenient form involving exponentials by using the logarithm. So I get this is e to the x it minus log of 1 plus t squared dt, okay? So that means I can define rho of t as it minus log of 1 plus t squared, okay? Now the critical points of this are going to be where phi prime of t0 is equal to I minus 2t0 over 1 plus t0 squared is equal to 0. In other words, where t plus or minus is equal to I times minus 1 plus or minus the square root of 2. Okay, and these are going to be saddle points. Okay, notice there's also singularities where t is equal to plus or minus I. Okay, if I plug that in, we have divergence of our log function there. Okay, but we're interested in the saddle points here. Okay, so if I take d to the rho dt squared, evaluated at t plus or minus, then I get minus 2 minus plus square root of 2, okay, which is not equal to 0, okay. So I can just expand up to the quadratic term, right? If this is 0, you have to worry about, you know, expanding out to quartic terms or something like that. Okay, we can just worry about the quadratic expansion in this case, right? Well, let's just focus on one of these saddle points. We're gonna have to deal with a couple of them potentially, or maybe rule one out if we can. Let's consider t plus, which is going to have d2 rho dt squared t plus. Okay. So in this case, I end up with 2 plus the square root of 2 times e to the I pi. Okay. So I'm going to write this out in terms of polar coordinates so that I can identify the direction of steepest descent in polar coordinates from them. Okay. So using my formulas from before, my steepest descent direction, right? This is my alpha, which is pi in this case. Direction is going to be theta equals a minus pi over 2 plus pi over 2. This is equal to 0. Okay. And we also have minus pi over 2 plus 3 pi over 2, which is going to be pi. Okay. So those are my steepest descent directions in this case. Let's now draw this out. And I think I'm going to do that on the next slide, so I can show that diagram as I deal with a couple other things. Okay. But these are my steepest descent directions, right? So there was the argument before, I just, I plug in at my alpha here, and you just plug and chug and you get back these values. Okay. If we draw out the integral that we're interested in, I'll write a UV plane here. This is imaginary part of t and real part of t. Okay. Here's my point that I'm interested in, I times the square root of 2 minus 1. I've now said that my steepest descent directions are here and here, right? The 0 angle and the pi angle emanating from there. So now we can see this sort of deformation that I want to do. I want to deform, and I want to kind of join up the steepest descent direction out at infinity. I want to join that one up out at infinity, okay? And just for fun, let's look down here. There's a point minus I down here, and then on the other side of it is this point t minus, which is equal to minus I square root of 2 plus 1. So I'll talk about that point later, but it turns out we can ignore that point and just involve this point here. Okay. So Cauchy's theorem tells us that if we draw this line C1 and we draw this curve here C2 and we connect out at infinity there, we could do that. You can always just say, well, let's stop at some r that's really large and join them up and then take the limit as r goes to infinity. Okay. And it's a leading order approximation, so that's fine. The integral over c minus the integral over c1 plus the integral over c2, right, is going to equal 0 because I have no singularities on the inside there. Okay. This is Cauchy's theorem. Okay. The singularities are all outside of there. And so that means that the integral over c is equal to the integral over c1 minus the integral over c2. Okay. So now this says, well, I just have to compute the integral over c1 and c2 in this case. And notice that the other saddle point t minus has some imaginary part t minus, which is going to be less than 0. So it's outside of there. Okay. The function e to the I xt has magnitude equal to e to the minus the imaginary part of t in this case. And it's going to that's going to grow exponentially in the left half plane, okay? Because if imaginary part is negative, I get this exponential function that's shooting off, okay? I of x is equal to, or approximated by, actually it's equal to e, the integral over e to the x rho of t dt minus the integral c2 of e to the x rho of t dt, okay? And following the same procedure as before, I have the integral from 0 to epsilon e to the rho of t plus r x dr minus the integral from 0 to epsilon of e to the rho t plus minus r x integrated with respect to minus r, right? Because we're just going in to the right and to the left here for each of these integrals, right? I'm integrating with respect to minus r to the one on the left, okay? This means that I of x is approximated by e to the xi imaginary part of rho of t plus the integral from 0 to epsilon of e to the x real part now of rho t plus r, okay? And remember, I can do this because I've chosen a steepest descent contour. And along the steepest descent contour, the imaginary part should be constant, okay? The real part of rho should be descending as rapidly as possible, okay? The other integral is the integral from 0 to epsilon e to the x real part of rho t plus minus r dr, okay? So we're almost there, okay? We just need to use the typical Gaussian integral approximation, okay? And we can do that if we evaluate the real part of rho at those points. Where's our rho here? Here's our rho, okay? If we plug that in for that particular value, we'll go through the intermediate steps. Then we're going to get an r squared term popping out if we apply Laplace's method, okay? And we get I of x is approximated by the square root of 2 pi over x 2 plus the square root of 2 e to the minus x square root of 2 minus 1, 2 times the square root of 2 minus 1 to the minus x as x goes to positive infinity, okay? So this step, when we got to here, that's essentially just applying Laplace's method, okay? Like we've been doing a bunch before, okay? The new part in these calculations is really choosing this particular steepest descent contour, okay? But once you've done it a few times, you see that it just amounts to finding, okay, where you have a critical point, okay, and where the angle emanating from that critical point satisfies this relation, okay? Just whatever your starting angle is, okay, for where so whatever your second derivative value is, okay, you pull out the angle from that in terms of a polar coordinate description, and take the negative of that divided by 2 plus pi over 2 and plus 3 pi over 2 in that case. Okay. So this is our leading order approximation. Okay, we only needed to use one of the saddle points because we could create a closed contour using just that single saddle point in that case. And it turns out the other saddle point was a bad one to choose because it's on the other side of a branch cut of our original complex function. Okay. So so that's another example of using steepest descent. Okay. Are there any questions about that example? Okay. I'm going to do one more example, okay, to try and just crystallize this further. And then we'll be done with integrals, okay? So let's take the following example. Integral from 0 to 1, e to the minus z t squared dt. Okay. Now it turns out there's two ways to approximate this integral. First of all, for small z, okay, you could expand the integral in a Taylor series, okay? So e to the minus z t cubed is equal to the sum from n equals 0 up to infinity minus z t cubed to the n divided by n factorial, okay? And then integrate term by term. And then you'd have that I of z is equal to the integral from 0 to 1, a sum from n equals 0 up to infinity minus z t cubed to the n over n factorial dt equals the sum from n equals 0 up to infinity minus z to the n and factorial, and then from the integration we have over 3n plus 1. Okay. Now this is fine. This is actually convergent everywhere. Okay, but it's going to be super slow for large z, right? We have this algebraic expansion, and as we see typically for something like Laplace's method, stationary phase, method of steepest descent, usually we get transcendental terms that you can't really get using these just term by term expansions, okay? So it's going to be slow, it's going to be inaccurate, but it's going to be right as long as you take enough terms, okay? Now, as we've shown, right, if we want a better expansion for large z, we have to do a little bit more work up front, and that's using steepest descent. And we'll define z as magnitude of z e to the I theta, okay? So I of z is equal to the integral from 0 to 1 e to the minus magnitude of z e to the I theta t cubed dt, okay, for z large, magnitude of z large. Now we can show where there's a saddle point in this case. Our rho of t in this case is going to be equal to e to the I theta. The minus sign here, t cubed, okay. Rho prime of t0 is going to be equal to minus 3 e to the I theta t0 squared equals 0, wherever t equals 0, okay.